So this is the first video of a knot, a typical knot that's being made. It's a bit shaky, like as I mentioned, we haven't edited yet. So the tripod is just a temporary support, so you'll see the guy working through it. Here you go.
Clap.
如果唔係我，如果個難題我可以講一講教。
OK 啊呢個。
排列三運，西正。
So, can you guys still hear me when I am in this presentation mode? Yes, right?
Yes.
Yeah, okay. So let me just scroll through it again so you see what happens. So these black wires are nylon with glass fiber reinforcement inside. So they used to do this with actual bamboo skin. The bamboo skin is super sharp. Like if you peel it into strips, it really cuts your fingers. So back in the day, the bamboo masters, they had like really thick calluses on their fingers from doing this. Now we all have delicate computer hands. So even the scaffolders are prefer to work with these types of connections. So the first thing that you see, they position the sticks correctly, and then you put the wire in the back, you hold it with one finger, and then you fold it forward, and you make sure that the wire doesn't go over each other. So you put the strips next to each other. And then, let me see if I can show it. Yeah, so the strips are nicely next to each other. Theoretically, you make it as tight as you can. And then you wind it a few times around until you have like a nice flat part in place. And then once you're there, then you pull it, so you yank it as tight as you can. And then you grab the wires with your fingertips as close to the column as you can. And you squeeze them hard, and so that's the left hand. And with the right hand, what he's doing is also squeezing it hard. He's basically spinning, like twisting the wires. He's winding them up. And what's happening as they're winding, the plastic actually deteriorates a little bit, and it really grips into each other. So the plastic kind of cuts into itself away a bit, and the wire becomes more of a thick, almost like a woven rope, as you can see here. So that's because of the ripples in the plastic and the glass fiber inside. This doesn't slide loose. This is not a slippery material. So with that, you're basically locking in the tip of this winding where my mouse is, and then what they're doing is, so that's what you see here. So the knot will not slide off easily anymore. And then what they do, they add tension to it by putting the plastic wires through the openings that you have at the bottom, and then basically pulling it hard, like yanking it, which is what's happening here, underneath or in between the bamboo and all the wires that you have. So here you see that this is actually tightening the knot even further. So by yanking this in, it actually adds another material in between the knot itself. And that's one way to make a very tight bamboo knot. So let me just play that again from the beginning so you see it.
Clap.
如果唔係我，如果個難題我可以講一講教。
OK 啊呢個。
排列三運，西正。
Now, this is a bamboo master doing it. I can guarantee you if I were to do it, or if you would do it without experience, it would take you quite a bit longer to get it super clean the way he did. But that's him doing it in a relaxed way. Like when they're on a construction site, they're doing it even faster. But what you can see here is what I was mentioning earlier. Like if you were to move this stick in this direction and this one down here, then the knots will become a little bit looser. If you rotate it in the opposite direction, then it will tighten itself up. What's also interesting here is that the master is actually using the ribble in the bamboo, like the thickening that you have here, to basically lock the whole thing in place. Because the bamboo gets thicker here, the bamboo itself wants to rotate in the orange direction, which is tighter. The blue direction actually will result in greater stiffness because the thicker piece of the bamboo would have to roll over the other one. But this, of course, you can only control for your first connection, because as you go further down in your pipe, you don't know where the knots are. But so that's one of the rules of thumb that they're also applying when they're building these things. But that's really to plan where you have your knots in your bamboo structure. That's almost, it's theoretically possible, but it would be an unnecessary, like kind of ridiculous endeavor, I believe, to push it that far. I'm going to show you a few other videos of different knots that they have. So hold on, let me open up this one. So this is a different connection. So this is a typical connection, an open hinge that's used most commonly, but they have different knots as well for different occasions. So let me see this one.
Okay. Ready to go?
So this is to make a cross connection.
Okay.
So they first fix the bamboo at the base. Yeah, sorry, we haven't gone through all the footage yet to get the really clean, good ones. So that's just a fixed connection at the bottom pole right now. The knot is placed at the bottom. And then they'll do the same with the one on top. And basically that knot in the middle will become a very, very flexible hinge. So this is a type of connection that they said that they would use if you want to make a pop-up grid, because now there's no shear rigidity in the middle parts at all. You can just rotate your columns very flexibly. So here there's no orientation to the knot really. And so that's a super flexible knot now that you can just hinge basically over each other. And the next video, yeah, you see, so that's a hinge.
Right. Okay. Yes.
But that's very uncommonly used. And now here they're going to make a rigid hinge. They first fix one diagonal, almost similar to the first knot that I showed you earlier. And then they go to the other diagonal. And you see that this is a much stiffer connection. So this is the type of joint that you could use to fix your diagonals, for example, on top of it. And then they tighten it by, yeah, choking the neck basically between the two columns. There you go. And that's kind of your rigid connection that's not supposed to be able to move too much. And then I think I have one more video, or maybe that's of the same. is again the hinge connection that I showed. Yeah, that's the same loose hinge connection that I showed you, or the second one that I showed. There you go. There you go. So you see these knots kind of represent the techniques that we're also simulating digitally. Yeah. Cool. Any questions?
Yes.
Go ahead.
How reliable are these nylon ropes?
They build scaffolding that go up 400 meters for the towers that they're doing here, so it's very reliable. What do you mean by reliable, actually?
So the structure will have some lifespan, and because it keeps twisting and with friction, I'm assuming because some of the nylon ropes that I've seen, they tend to wear and tear over time. So does that?
Yeah, they are for temporary structures. So in Hong Kong, legally, it's not allowed to build permanent bamboo structures. So these are for temporary structures, but they can stay up for quite a while. Typically, when a scaffolding is built, the master is responsible to every 2 weeks go up and inspect his own structure, and if he needs to replace things, then he needs to replace things. Let me pull up a very fun photo. Hold on, you're gonna like this one, just to show what it can do. Hold on. I wanna. All right, come on, open up. So, but the bamboo wire originally was better in a way because it behaved exactly like bamboo would. So nowadays, these nylon wires, they behave slightly differently. But that's why in the ZCB Bamboo Pavilion, we used metal wire because that has a longer lifespan. Come on, computer. Okay, I have the folder here, but I cannot see the photos that are coming up. 1 second. Okay, hold on. Here you go. Share. This was after a typhoon happened in Hong Kong. This is like a 10-story scaffolding that came down from the side of the building here, and it was peeled off, and it didn't collapse. So here on the bottom, you see sometimes they make these little temporary.
We don't see the photograph.
Oh, you don't? Hold on. Let me share again. I'm probably sharing the wrong screen. Are you seeing it?
Just a minute. Yes.
All right. So this is one of those temporary support scaffoldings for facade renovation, and a typhoon passed by and it basically ripped the scaffolding off of the building. And you see that yeah, the bamboo is breaking and it's cracking, but all the ties are still connected. So yeah, it's actually, with a steel scaffolding, this would have been a disaster. It would have collapsed and it would have come down and would have killed some people. So the material is quite unique. But yeah, that's a diagram of the knot that I just showed. But in Hong Kong, yeah, all these towers are built with this type of temporary scaffolding, and yeah, that's the knot that they use for it.
There is a question in the chat by Enrique.
Yes, the material this connection is made of. So this is it's a nylon wire with glass fiber inside of it. It's very cheap. It's mass produced. It's totally unsustainable because you cannot really easily recycle it. They just trash it afterwards. So that's a pity. But it's more friendly to use in terms of the bamboo skin that they have used for centuries requires just more manpower to produce. You need to take your bamboo, you need to peel it off, you need to. So this is just cheaper, but not more sustainable. In other parts of the world, I know in India they're using typically a hemp rope. In Bali, they also use rope. Very often they also bolt or peg combs together, but then you have a very different connection. So the types of shells that we're talking about here, they kind of require a loose connection. You can make that with a bolt as well, if you want to. Like we did a study at some point where, let me quickly sketch here. We would use like a metal spanner, you know, these little metal spanners that you have that allow you to basically, yeah, a little metal spanner here, and then we drilled a hole here, made a rivet in between it, and then put another metal spanner on the other side, basically. And then we connected two bamboo poles like that. That works because you need something that's flexible enough to absorb the diameter of the bamboo. That works as well, but I don't know if it's definitely not faster unless you don't have the skill to make these knots. Like if you don't have the plastic wires or if you don't know how to make the knots, this is also a way forward. This is fireproof. This is also doable. So you can engineer your own little pieces, and we've done this in the past as well. That kind of works.
So this can be applicable for more permanent structures that are going to be built in bamboo. Because in India, I know that they are making some codal changes and they are trying to introduce bamboo as part of the construction guidelines.
Actually, sorry, I should have shown you. I have one right here. Well,
this is amazing.
Yeah, we experimented with that at some point. We added a little spacer so that the knots would not clash against each other as they're going around. But this is one way, and because you can screw it up, you can tighten it around the bamboo. Problem that we started to see here is that the bolt was actually cracking the bamboo locally if you would make it too tight, which the wires don't do. So metal is much stronger than the bamboo itself. So it works, but it's not ideal actually. There's a natural evolution that the trade has gone through that kind of arrived at these nylon wires, and that works quite well. So the nylon wires is not developed by us. This is something that the bamboo trade has used for the past 30, 40 years. I don't know who came, but it's coming from the construction industry here. Okay. Any other questions about the knots? Okay, Aman, you were trying some things out of the break. Do you want to share something there, or?
No, I mean, I didn't work on it further during the break, so.
Okay.
If I manage to resolve it, I'll definitely share.
Sure, please do. Hold on, let me then close all my photo screens that I just opened up, and let's go back into Rhino. Oh, sorry. Let me share screen again. So yeah. So what are we? We're at file B. So at the end of file B, yeah, you basically have your nicely interconnected curve network there. Let me close this one, and I'm just going to open up file C, which just builds up on that. It's running. So here, well, now you see what you would get after yeah, so this is our setup with the triangular stuff over here. This is what we get when after my whole setup in the beginning, I've just basically added our earlier Grasshopper script with the zombie function and the rods, using the standard rods to arrive at the outcome that you see here. I'm going to run that again. Yeah, it's taking around. It's going to take around 30 seconds to get things back into shape. But let me improve a few settings because I have way too many control points here. Let me bring that down to 2. Oh, there's actually a little mistake in the script here. This value is too high. I don't need to subdivide each segment into 9. I'll just subdivide it into 2, so that will speed up things. And I'm going to increase the resolution that I had here in the beginning to, let's say 10. And let's see how fast this one goes. If I run this one. I remember back in the day when we did the ZCB Pavilion, it would take half an hour for it to find a solution. So that took quite some time to kind of get through it, but that was with Kangaroo 1. Kangaroo 2 is a bit faster at doing large calculations. My computers have gone faster a little bit as well, but it's still not fully real time. Let's see. Maybe.
Do you think it's because of the combination of Anemone and then the solver both happening simultaneously that is taking so much time?
Well, they're going consecutively. So once Anemone is done, then it's just Karamba. Then it's just Kangaroo that takes time. So, oh, interesting. This one flattened up completely, and it didn't reach. It didn't finish all its 100,000 iterations. That's interesting. I hadn't seen that one yet. Hold on. Let me switch this one off. It's flattened the whole thing because of my top surface that I added here earlier. So what I'll do, let me lock this one. I'll make this one 8, and I'll delete the surface. You can, like, what you just saw was the natural balanced shape of this geometry without any anchors or any forces pulling at it. That's like, that was a neutral shape. Once you start to include anchors in the whole setup, the shape's going to be very different. But now without that back surface, you'll see a very different end resolution coming out of it. Oh yes, and that was much, much faster now. So now we have a very nice and balanced little shape. Let me see what happens if I bring that one back in, if it's again going to flatten out, probably. Okay, yeah, so this one seems to be working very nice. Yeah, it's similar effect. Okay, Nightic, you shared, let me just share this one. This pavilion here, this is not built, this is a render. We reached out to the competition organizers to sue this guy because what we did at the office way before that competition had taken place was design this one, which is exactly the same thing. They just rendered it different and then they won the competition, but they never got it built. And the competition organizers said that it was different enough that it wasn't plagiarism, which is absolute bullshit. This is totally plagiarized. But in this, our design here, we didn't know anything about Bamboo at the time, so there's nothing really in there. In this one also, there's no, this is not possible. The way it's designed here with the curvature is there, it's not possible. This is just a render. It's a nice one. It's nicely done. But yeah, I fucking hate it.
That is why I sent you, like, I'm not sure. Okay, how could they get this much curvature?
No, it's not possible. With bundles and it's the heat bending, you can. Even in ours here, you see the orientation is done differently so that there's less curvature on the stick. So ours theoretically should be possible. We were asked to build this pavilion, but then they didn't have any budget for it. So in the end, we couldn't afford going ahead. But these guys, it's the only thing in bamboo Luca Poyan has done that I know of, and it's a ripoff. So yeah. Yeah, hits a sensitive nerve. So yeah, so this is fun because now we can start to play around with this a little bit. But if you want to, we can easily add some anchors to this setup. So let me just quickly do that. If I make a new layer here, anchor, and I'm just gonna add a few points in my mix here. Just 3 points, say one here, and one here at the bottom. And oh shit, every time I hit any button, the zombie's gonna recalculate. So you have to wait a second. I should have locked this. All right, sorry. Come on. I pressed it 3 times, so it's going to do it 3 times now. So what I was trying to say, this is the starting point where you then can start to really design with it. You can pull your edge surfaces below the ground. You can fix anchors. Like from this point onwards, it really becomes a design exercise. Okay, let me lock you. And let me add, so geometry, pipeline, all my points from layer, anchor. Just double check that I'm getting them. Yeah, and then we can just do kangaroo 2, anchor, and I'll bring those in over here. And immediately you'll see that the geometries will start to become very different. So what we did earlier with the bubble shape, trimming it on the ground or playing around with all of these things, you can do here as well. Hold on, what happened here? That surprises me. Hold on, I need to double check something. If those are actually connected to my curve, probably not. Ah, yes, there you go. My anchors are not connected to my curve, so that's why that's not good. Okay, hold on. Let me change that. Select objects. Well, actually, let's do it slightly differently. I should have blocked my kangaroo again on my rhino again. Okay, lock this one. I'll bring in my point lines here. Let me just temporarily bake these for a second. Group, yes. And I'll move my points to say, I'm definitely on it. Okay, now let's see how that goes. Yeah, this should work. And now you see a very different type of shell structure coming out of it. That kind of works. Now you're kind of controlling the whole setup in a specific way. Just like before, I can add, let me switch this off for a second. I can add wires to it and pull this whole thing down. So now you're back into like a normal Rhino terrain where Yeah, let me try something. What if I add 2 points? Well, the sky is the limit. You can very easily add or remove surfaces and start to play around with it. So that's kind of the main goal of this exercise is for us to actually create a design tool, right? So with this, you can very quickly start to design. The tools that we use for the bubble shape to cut this on the ground plane can be applied here. Yeah, that basically becomes a setup. No difficulty there, right? No questions there? No.
No, all clear.
Okay, cool. Then the next thing I'll show you is how to incorporate your mesh in this as well, because the skin does become something that you will need. Hold on, let me simplify this back to our original shape here first, and I'll get rid of the anchors and of what we have here. Okay. There we go. All right, so I'm going to open the D file now, where we have the mesh in there as well. So here, while it's running, so you'll see first, again, the hoops, the anemone part is running, and then the zombie will run. So what we often do is we build in these safety breaks where I put these vertical black lines, we will bake an internalized, we'll internalize geometry inside the buttons so that it doesn't always have to rerun fully. Now it will always fully rerun. So the main goal here is to arrive at this setup where we have the skin, the mesh in place as well. And the reason why we need the mesh is so that we can create the offset of our curves in the U and V direction. So if we want to calculate the thickness of the layers of bamboo that we have, we need to move things normal to the membrane that would basically connect everything. So that's why it will become important to have these membranes in place. So how did we do that? Pretty straightforwardly. Let me switch this one off for a second so I don't run into trouble. So from the very beginning here, I've taken two values. I've taken my surfaces here, which are all my input surfaces that I have originally. And I've taken the number of subdivisions that I have as a variable over here. It's because that defines the diagrid that I have in the beginning, right? So with that number, you're basically controlling the diagrid that we have over here. So what I need to do is I need to make sure that my mesh that I produce actually has, so if I turn this surface into a UV mesh, I need to make sure that I have, this wire doesn't need to be, that I have my points exactly overlapping with the points of my diagonal. If I don't have that, then of course my mesh is not going to work. And I'm going to keep my mesh as a quad mesh. So it's going to be positioned in terms of its topology 45 degrees to my main column direction, basically. So here I have a slider that basically allows me to refine my mesh more or less if I would want that. But this is actually the minimum that we kind of need. So we're going to bring this into Rhino together in the show button, together with the other geometry to be processed. But there's a few issues here. If I, let me see, if I look at this, so the red lines are my bamboo columns that are being evaluated. But you'll see that on the corner point, for example, I don't have anything supporting that corner. So my mesh will become very floppy there. Also in the middle here, my intersection point that I have there is not connected to any of the points of the bamboo diagrid that I have. So I do need to add a few other members into my whole setup here. So what I've done is I've basically written a script that puts a very, very soft stiffener around the edge of the bamboo, of the surface, to basically catch all of these points. And this edge tries to straighten itself out so that the corners that we have here don't become too loose. And I made it slightly elastic so that it shrinks down a little bit, so that when the diagrid becomes from square, it becomes more diamond shaped, that the fabric will join in that deformation. So it's a pretty straightforward setup. So the way we've done that, well, first I turned this whole thing into one single mesh with unified normals. So my mesh it's no longer in this case, what is it, 6 surface patches, but it's one continuous mesh. First thing I need to do then, hold on, let me hide. Where are my curves? Here. So I'm getting my naked edges, which are these, the green ones on the outside now. I'm getting my naked edges and I'm exploding them. So what I need to do here is I need to make sure that, so right now the naked edge button produces a separate line segment for each and every one of them. What I need to have is a continuous line here and a continuous line here and a continuous line here. And then here I'll put my my stiffening forces on all of the segments here. But I don't want to have a stiffening force in my corners, right? So I need to break up my outline into a continuous series of lines that are separated at all of my corners where I don't want to have a hinge. So it's similar to what I did earlier when I was making the mesh in the first exercise this morning. So what I'm doing here on the left is I take all my lines, I explode it into all of its line segments, and then I measure the angle. So I join it into one continuous curve, and then I measure the angle between each of the line segments. I could actually do this faster with the split that kink tool that I used this morning. Okay, different way of doing it, but it kind of works. Yeah, I could have split it at the kinks basically, and that's actually easier. Yeah, okay, different tool, different technique. Basically, what I end up with here right now is a series of 12 polylines, which are all these little segments on each side, and those I'll bring into a rod function similar to what I used for the bamboo columns itself. Only this time, their bending strength and their axial strength, I make it much less strong than the bamboo here, because I don't want the membrane to influence the overall equilibrium too much. So theoretically, I want these to be as small as possible. Then additionally, I'm going to give a tiny bit of elasticity to my mesh edges that I have here everywhere, so that when my bamboo, like that, for example, the points that I have here in the middle, so that they kind of flatten out as well, that the membrane basically gently absorbs the elastic behavior of the whole setup. So these two new forces are added into our equation. The geometry of the mesh is added into the whole show setup that we have here. And then at the end, I just need to, again, unflatten my tree, and I can extract my mesh on the side here. Let me just do that right away. Let me hide all of this. And let me switch this on. And as it's running, oh shit, I still have the curve density of 9 here, I think. I hadn't lowered it yet, I think. Let's see, might take a while to cut. I know. Yes, it is still super dense actually, so. Yeah, hold on. Let me, this mistake here is causing a lot of calculation that are not necessary. Put it 2 or 1. Wow, let's put it 2. Now it's going to go a little bit faster. Arrived at a slightly different shape. That's interesting. Well, I mean, the resolution there, you know, that's from the first class. That's where we control how precise this thing is. So what you see now is that the mesh still has a sharp corner at the bottom here. If I were to switch this off, let me just hide this one, and then you'll start to see the difference right away. Now my edges are all messed up, and if I don't do my elasticity in there, then it gets totally messy in the middle parts where here, let me switch this on. where the fabric is actually moving around a little bit. So you do need to have these two in there to arrive at the final outcome. So that's a very nice way to continue your membrane from it. Like theoretically, you could use this mesh now that we have at the end to create your fabric strips. Like you can triangulate that according to diagonals and then flatten it out and use that to pre-cut your fabric strips that you would then use to clad the whole pavilion, depending on what type of material that you want to put over it. But this is a quick way to calculate it. No questions, I guess? All good?
One question.
Yeah.
The edge length, and you're reducing it to simulate the fabric. Does this and the base bamboo structure correlate exactly on top of one another?
So right now, because that's why in the very beginning, I had to make sure that, hold on, let me show that. Here in the very beginning, my mesh edges that I have here and my bamboo lines that I'm working with have to share points within the tolerance of what the zombie solver is working with. And right now, these points are exactly on top of each other, so Kangaroo will merge them together and treat them as one. And therefore, yes, the mesh now follows the bamboo correctly. If I were to define my mesh differently in a way that my points would not fall on top of it, then they would just become two separate objects that don't behave together. But Kangaroo fuses everything together.
Okay. My question is, because these points are correlating, then there is this additional force that is acting that wasn't acting earlier, which earlier the edge lengths were not supposed to reduce in size.
Yes.
It's supposed to stay constant. And that's when we were using the spring force with lines. Now that we're using mesh edge lengths, and with a length factor of 0, it's automatically trying to reduce the line. So not all the individual line segments on your mesh are not of equal length now.
I agree, yes. So
does that matter?
That's where the so yesterday we talked about the exact or relative nature of these values. And that's where the relative nature comes in. The elasticity of the mesh is only 1,000th in terms of strength from the bamboo. So where will this really play an effect? For example, on this point here, which is totally not connected to any bamboo area. So here, this point will automatically place itself in the smallest distance in the quad that we have here. But the point here that's on top of two bamboo sticks will hardly feel any influence from the mesh elasticity.
Understood.
So that's why it's very important that these are very, very low. And the rod edges here, I gave it a slightly higher value, and there's no exact science there. It's about playing around with it and seeing what works. Now, that's why it's important to always keep track of how close you are to your original lengths for your bamboo poles. Here you see, well, we're starting to get 2% off, 2.5%. That can start to become considerable. So you just need to be careful there that your equidistancy doesn't get sacrificed. But with the knots that you just saw, if we work with the hinge knot that they have, the knot itself has a bit of thickness as well. So that allows the columns to move a little bit over each other. So even if the equidistancy is not 100% maintained, the system will still work on site. It will not be exactly what we predict here, but it will be within the realm of what is practically possible on site.
Okay.
So there's it's all a balance of predictability, control, and letting go, and allowing the material to find itself. And that's innate to the bamboo material to work with.
Okay, understood. Thank you.
Yeah, it's an abstraction. It's an abstraction of the behavior that you would have. But as we've shown in some of our build projects, it's close enough to allow you to actually move ahead on site with it.
No, absolutely. I completely agree that Kangaroo is a wonderful tool. And this particle simulation helps us approximate forms which otherwise would be very difficult to do it ourselves.
Yeah, exactly. Yeah, I mean, that's why I think that's one of the things that limited Friotto back in the day in his explorations. That's why the geometries were so restrictive back then. These tools theoretically should allow it to open up quite a bit again. All right, let me go to the next one, which starts to include the offsets. And that's the last one that I have prepared for today. It's a little bit longer one. I locked it because I'm going to make sure that I didn't make any mistakes here. That's set to 1. That's set to 10. That's fine. So now, actually, I did prepare a few other ones. Yeah, let me drop those in the file chat for now as well. These are just 2 general files. I know we can talk about those in a bit. I haven't shown those yet. Just Bamboo visualization and curvature analysis, nothing too special there. And so what I'm going to do now is I'm going to work on the offset of the layers, which in the bubble diagram that we made at the beginning is actually quite... Oh, sorry, I sent this to you, Aman, privately. This should go to everybody. Sorry, my bad. There we go. Everybody should have them now. Yeah. Let's first go to this one. So in this one, the aim is to create the offset of the members that we're working with. But in a bubble shape, let me just sketch for a second. So in a bubble shape, it's pretty straightforward because we know exactly what the U direction is, we know what the V direction is, and we know what the diagonal direction is. So we already have our data very neatly worked out. We know exactly, it's just a matter of offsetting. So there's nothing really difficult there. I didn't prepare it for today, but I can imagine that you appreciate it. There's nothing difficult there. Here, however, this starts to slightly change because we don't know yet clearly what the U direction is and what the V direction is, because all these curves have been interconnected again, and they don't per se stick to the original logic. So this is where it gets messy. This is where it becomes very ad hoc, where we've been developing tools that work for one project, but that won't work for everything that we're doing. So, and this is also where potentially you need to do things manually if you don't want to run into trouble. Like this is the point when the universal script doesn't work too well anymore. But so we've written one solution that works for this setup that we have right now. So let me talk you through that. So the first thing that we need to have as an outcome is indeed our, hold on, let me make sure I switch on the right things here. We need to have our curve network and our mesh. And then the first thing that we basically need to do is identify the 2 sets. What is the set that goes up and what's the set that goes down? And after quite a bit of, and then we need to have the stick diameter as well. After quite a bit of trial and error, we've come up with this pretty ghetto sledgehammer scripting solution for it that uses sorting in a polar array, specifically for this one solution here, to sort out the members. So let me just talk you through it. Where we eventually want to end up is we want to know which curves are in the U direction, which in my case here are these, and which ones we consider to be the V direction as we're going across these singularities. And one of these 2 we're going to offset a little bit. So in the script that we have here, you'll see that one of these 2 is offset above the other one, and the other one is kept flat. Right? You can also do it for W layer, but then I didn't manage to finish that script by today. We have a draft of it. But so how did it's basically a sorting exercise. How can we sort these sets of curves now? And we used a polar trick for it. So let me go into top view here. There's a very clear star-like logic here. So what we did is I took the average of all my points of my curve network, put that on the ground, and that's the center of my polar array. And what I've then done is I've evaluated the middle parts of all of my curves. So these are all the middle parts of all of my curves. And then in this polar coordinate system, I can figure out what angle these are at. So if I put a polar coordinate system here, I can basically measure the angle that all of these points have in my polar array space. So that's what I'm measuring here on the left with the angle here. And then I can sort my curves based on that. So what I've done here is I've sorted all of my curves, and you see 0, 1, 2, 3, and then it jumps 4, 5, 6, 7, 9. Like you see, theoretically, these should all be the same value, but there's a little bit of tolerances creeping in there. But there's clearly a group of the first 8 or the second 8, is it 8? 9, second 9, third 9. So what we can then do is we can partition this list based on, in this case, the 6-fold symmetry that we have. And we can partition this list. I'll show you here. And here we have a little bit of dirty calibration possible to move the whole list left or right. But basically what I've done is now I've split it up into branch 0, 1, 2, 3, 4. So now I have my clean branches 0, 1, 2, 3, 4. And then I just need to parse this into branch 1, which is all of these, all the green ones, and then branch 2, which is all the red ones. So now with this polar array sorting, I've been able to sift all of my curves into 2 groups that are not intersecting with one another. That's essential. Hi, come on. So now this is my one group, and that's my other group. So one of these I'm gonna offset, and the other one I'm not. So then from then it's quite simple. How do you offset? So I get all of my control points. I find there's different ways of doing it. What I did is I used the line segments and I evaluated their center point. And then I found the closest point of that center point to my mesh, which you see it's not an exact science here. And then I moved, what am I doing here? Yeah. Oh, so, right. Let me just double check what I did here. I actually used the face normals. Weaverbird, okay. So what I did is I exploded my mesh into faces. So actually, yeah. So you see that each point is kind of in the middle of one of my mesh faces. Now I'm extracting the face normal of all of these faces here. So what I'm doing here is I'm identifying which face each point is the closest to. I'm extracting the mesh normal in that one particular location. And then I'm moving my points based, my control points here based on that. I'm moving my line segment, sorry, based on that normal vector. And then I'm basically, yeah, taking some of the points. So I'm taking the starting point, end point, and then end point, end point, end point from all of my curves here. And then I'm redrawing a polyline that kind of goes through it. So you see I'm taking the starting point, starting point, starting point. And that way I'm basically redrawing my polyline as an offset of my original mesh. And that's it. So here in the beginning, I can now control my bamboo thickness very easily. And the whole setup, yeah, kind of follows the surface quite well. And it's in areas like this where there's a change of direction that you see that that becomes important, that we work with the mesh normal rather than the normal vectors in a particular point here. So this is, it's kind of a quick way to make that work. That's it. Oh, let me keep that on. And yeah, any questions there? So once we have that, well, then we have our offset curve network. And then with that, we can then easily, again, if we want to explode our curves and turn that into a NURBS curve, which brings me to my next point. So there we go. So now we have a continuous line network going that is nicely offset from one another. And on Friday, tomorrow is a bank holiday here in Hong Kong. On Friday, I'll show you that we can then very easily put our vertical connectors in between for our kangaroo setup that I mentioned to you yesterday. So now we have our bamboo setup nicely offset. And these you can then, if you want to pipe with the radius, that would be the same as your bamboo thickness. Oh. Let's see. There we go. And all my pipes are just tangentially touching. I need to half this one. There we go. Now you see all my pipes nicely touching each other. Yeah? Easy. But that's why it's important to make sure that you get your mesh through it as well, because you need it for your normal vectors. Okay, let me show you two other things. One, the curvature analysis. So in the button that I just gave you, it's just a random curve network that I have here. Let me just talk you through the curvature analysis. So what I've done here, I'm just visualizing this curve network based on the radius that we see. So for any, the way you would analyze curvature is you discretize your curves to which segments that you want to evaluate. I did use one button here, which is coming from the Human plugin, which allows you to show line weights very easily in perspective. So right now, this is going to slowly thinning out towards the back. So it's just a Human button. Don't worry about that. But basically, the way this script works is, yeah, we subdivide our curves into segments. Let me just take one from it. This item. Oh. So let's say that we're working with this segment here. Zoom. Then we'll do a curvature analysis of it. So a curvature analysis draws this massive circle over it as an outcome. So that's a circle that you have. That basically, if you then deconstruct that circle, it gives you a radius as well. So then it's just a matter of inverting this around. So an infinite radius means that you have a curvature of 0. A 0 radius means that you have a curvature that's infinite. So you have to flip it upside down, basically, which is what I'm doing over here. And then I'm doing two things here. I'm doing a color evaluation. So here on top, shouldn't have shown that. I'm visualizing all of these segments with the color code that I have identified here. And currently I've made it a hard color gradient. So any radius, any bending that's with a radius that's smaller than 1.5 meters will be shown in red. Everyone that's more than 50 meters will be shown green. And why this one is turning red is because some of the pieces are straight, like here at the very end, the piece is totally straight, which means that it's not a circle anymore, it's actually a straight line. So it becomes an infinite radius or a 0 curvature. But I've also here at the bottom done my bounds of all of these radiuses. So right now it's actually showing that the tightest radius that we have is 2 meters and the maximum one is close to straight. That's why this one is becoming red over here. So this tool very quickly evaluates how dangerous your structure is. Because you can just take your material on site, bend it until it breaks, you measure the diameter when it started to break, and then immediately you'll know what you can do. As I mentioned yesterday, one of the tools and the techniques that we are testing, I don't have any exercises prepared there, but the concept is quite clean, is to put a center point in our kangaroo setup, to basically work with a center point here. Oh, come on. And give a certain radius around that, like a sphere. And then every line segment that falls within the range of that sphere, we would give a different, we wouldn't restrict its length. Because what I'm trying to say is we would prefabricate the singularities separately. in a non-equidistant manner. So you can isolate these members that you want to prefabricate ahead of time. Don't give them a constraint, and then you'll see that there's a different type of relaxation happening in your singularities, which allow it to be buildable from thicker bamboos. Or you can also isolate it, keeping this setup, but then later on in Karamba, giving your bamboo elements that are here a different weighting that works too. Straightforward, right? So these are just very simple guides. In the final tools that we're going to be working, that we're working towards, we're going to create these setups where this data is published to the remote control panel. So I don't know if you know that, but Grasshopper has this very fun little thing where you can publish your data to remote control panels, and also your toggles or your buttons can be placed in here. So if I would also publish this one here, then I can toggle this one on or off over here. So this allows you basically to work better in a team, where in real time you can see whether or not your bamboo falls within a certain range, or you can give controls to somebody else. Yeah. All right. Any other questions on this?
I'll let others take up questions before I take mine this time.
Anybody? All right, Aman, you're the one. Go ahead.
Curious about a couple of things.
Yeah.
Really fascinated with the workflow. I'm going to explore everything within today and tomorrow.
Yeah.
And do something with it. So when you this workflow can also be adapted for metal structures. I understand that metal doesn't have this restriction of the elasticity and all as bamboo does.
Yeah.
But whatever forms we generate out of this, can we assume that the same can be done with metal sections as well, and it will be stable?
Metal. This requires serious. Hold on, let me open up a graph from yesterday. Let me get back to that. Let me show my last script that I have,
Okay.
and then I'll open my slideshow again to discuss a few other things. The only other thing that I have is a bamboo visualization script, which is a fun one. It's very, very basic, but it's what we've been using to produce very quick, nice graphics where it doesn't look like a line diagram, but actually looks like a bamboo setup. So here, oh. What's happening? Okay, while it's loading, I don't know why it's not refreshing. So, okay, here we go. So bamboo basically has a profile that kind of looks like that. Oh, bad drawing on the second one. But basically here there's a diaphragm. Here there's a diaphragm. So what we've done is you basically just take your axis curve and then you place circles on it. You place one circle here, one circle here, another circle here, another circle here, another circle here, and another circle here. And then you basically loft in between them. So we make one loft, which is going here. We make another loft, which is then going like this. And then we make a third loft that is going like this for each of the segments that we have. And then typically a bamboo has, if you look at its length, typically it will taper down towards the tip. Oof, bad drawing. It will become narrower towards the tip. And the spacing of your knots will be tighter in the beginning and then bigger as you go up. Those are kind of the graphic properties of bamboo. And we just scripted something that kind of does that. So let me first show it to you on, it's written for multiple curves. So let me just draw two curves here and I'll bring those in. I'll bring that in here so you can see it better. So here you see that in action. Not everything might even be in there, but basically, I have a simple thing during your constructions, typically you would put the narrow part on top so that the lower parts, which are loaded more heavily, become the heavier parts. So this first part here just basically flips your curves to have the tip on top. Then here we're defining the cell length of our bamboo, so how many cells we want to have. I think in this script we still have an even spacing. It's very easy to kind of use a graph mapper to make that slightly uneven. So that's the cell length that we have. And then we're basically populating, let me hide this one here. We're basically populating a series of circles around our bamboo setup. And here, this is where I would control the bamboo diameter. So actually that should become a slider. So now I can control the bamboo diameter that we're having. And then the delta of our inner rings that are going in between it. So how much that one jumps back in. And then those are the circles. And then we did a slight scaling towards the tip. So using the T value where we are on our tip, the T parameter on our curve, I'm gradually narrowing down the bamboo poles a little bit here. And then we're just joining in between them. So let me just show you these parameters in action. So if I look at this one here, if I make this one bigger, then you'll see that it's going to cut in much more, but that doesn't look realistic. So this is literally just a graphic exercise more than anything else. And then the tapering, I don't know if this is the tip or the end, but let me just pull this one down. I guess this was the end. The tip is over here. So now you see that I'm just gradually tapering things down a little bit. And this is literally just to make it look like a nice bamboo comb. Yeah, and as I mentioned, you can still shuffle the cell lengths a little bit more to have smaller cells in the beginning than you would have at the end. But it's a very nice, quick tool to produce things like this. Because what's nice in Rhino, if you why is this not showing?
I think you need to enable the preview, make it visible.
Yeah, no, it's blocking. My screen is blocked. And this is all done with NURB surfaces, so it gets quite heavy. If you want to have it faster, there you go. Then you go for meshes. But the nice thing about this one is that if you bake this, let me just bake it for a second. And then I'll just let it run in the background. Group, yes. This is a lot of geometry. If you do it as a mesh, then it will be fine. Now with the Make 2D button, if you can change your resolution, if you change your precision to something quite high and you do Make 2D with this in Rhino, you get really nice drawings out of it. Like really nice drawings out of it. So I'm going to close this one off. I'm just going to put this one here. I'm going to increase my unit system to be more precise. And then no questions about the script right now, right? From anybody? Okay, I'm just going to do a Make 2D of this thing then, and then that's going to take like 10 minutes to run, and I'll open up my slideshow in the meantime. There we go. No hidden lines, no scene silhouette, group outputs. Okay, I'm just going to run for a little while. So the question was about steel, right? Let me open up my PowerPoints. This one. So this system works well with elastic materials, which are in principle all of these only. Like metal and spring steel theoretically can also be used for it, but the forces that you will need to bend it are huge. So for a pop-up structure, you actually want to be If I'm correct, you actually want to be at the bottom end of this curve. So that's why anything that's kind of lower here or even lower here is probably the easiest. Like a plastic, like glass fiber reinforced plastic, which is like electrical tubing. With that, you can very easily make structures as well. They've built this temporary cathedral in France. Let me show you quick links there. A link there. 1 second. Créteil temporary cathedral. There's a very nice video here, I think. But they took the website down recently. Let me see if the website is still there. Well, this is a temporary church that they made from electrical tubing and swivel shackles. They were just placed flat on the ground with these types of swivel shackles. And then the whole thing was popped into shape and just clad with a fabric. And there's a, this is working. I'll just share, I'll share this link with everybody in the chat. It's a very nice video that you can have a look at. And that just shows, it was again also first the 2D grids and then the diagonals added afterwards. Here, construction. And it's done with the local community where, oh, they have photos somewhere, or gallery probably. Okay, so I knew something wasn't working anymore. Their photo gallery doesn't work anymore. But yeah, here they just use PVC pipes as a technique. And it's done again with a spring particle simulation system. So this works because the material is quite flexible. If you would do it with steel, the force that it would require for you to bend the pipes is so high that it would become very, very difficult to do. So yeah, here, that's the connector where they connect two poles to each other one on one. And the video is probably a bit choppy. Actually, let me stop share and share again with the video settings. So that will be better. And yeah, here you see they're working with standard swivel shackles to make the connections. And then let me jump forward a little bit.
I believe you're seeing the wrong screen.
Oh, you are? Sorry. Are you seeing it?
Yeah.
Okay. So there they had the whole grid prefabricated. And then they just used the crane, where are we? To basically hoist up the whole thing. And there you see how floppy and flexible it is. If this were a steel grid, there's no way it would bend so much. You see all the hinges adjusting in a similar way to what we just simulated. And then the whole floppy shell slowly brought into its correct location. They had pre-calculated where the foundations need to be, so similar to what we did. There's no singularities in here. So this is similar to our bubble shape again. Yeah, so it's very similar, just a simple outline. And then here you see them fighting to get the anchors corrected at the base. So this is a very precise setup. So you see they have a little bit of tolerance in the slots for their screws. Yeah, you see the deformations quite a bit. And then here they have already added all the diagonals on top of it. They didn't have anything of that in the video. So all the diagonals are added to fix the whole thing into place. And then the pre-calculated fabric is just built over it. And yeah, that's it. Super simple. Hardly need for any scaffolding. All the people that are working on there apparently are part of the local parish that work together to kind of help out. Personally, I think it's a beautiful system, beautiful construction site, but a very ugly architectural outcome, if you ask me. Kind of falls in the trap of sticking with all these bubbles, especially from the inside. Kind of looks like a temporary structure, but yeah, it's easy to expand beyond that. But that's with glass fiber reinforced plastics, which sits here. Hold on, let me share again so that you can see me. Which sits here in the material setup. So this is the material that Friotto used. And as I showed you, bamboo, yeah, depending on where you are, kind of can fall inside this entire range. Now, theoretically, if you have the tools and techniques on site, if you want to scale things up, then the only thing that changes is the load, really. And that's why carbon fiber reinforced plastics, theoretically, are very promising, because that would, if you work with these plastic pipes that are reinforced with carbon fiber inside, theoretically you can take, this is a logarithmic scale, right? So you can have this is 120, this is 1200 megapascal, whereas bamboo is only here around 120. So this is 10 times stronger, which means that you can maybe go 3, 4 times, 5 times bigger in size than you'd be able to go with bamboo. So yeah, the different material application is quite interesting. Aluminum sits over here, which is in a similar strength but a greater elasticity. So that's easy, relatively easy to build with in theory. I haven't experimented with any of these other materials, and it would be interesting to talk to a structural engineer to hear their take on what the impact of this graph is on the ease of construction.
But I think this can be really scaled up and in your application as well, where because you mentioned that the limitation in Hong Kong is that it's not considered in building codes.
Yeah, sorry, beautiful drawing. See,
yeah,
absolutely elegant. So yeah, yes, indeed. Like in a Hong Kong context, yeah, no, I agree. That's why this is actually not a bamboo workshop. It's
active bending structures.
It's a of hybrids, flatbed or layup bending active shell structures. Theoretically, it can be applied to all of these other things. But bamboo, the nice thing about working with bamboo is that hold on, am I still sharing here?
Yes.
I lost you guys. Okay. The nice thing about working with bamboo and with these design tools is that the software is easy. Everybody has it freely available, relatively speaking, at zero cost. The material can also be at zero cost. And what's nice is that the tolerances that bamboo require, like the approximation that bamboo requires from the design, the design needs to be tolerant towards the fluctuations that you find in the bamboo material. There's a similarity there between the material and Kangaroo and how it works, and that's quite nice. Like in a steel structure, I guess it would also work, but you would probably need to be much more careful about where you absorb your tolerances and how you design it. But there's no reason to think that it wouldn't. But with bamboo, it does right away, and it has the potential that you can build. The knots can very easily be taught. It doesn't require anything complex. So you can just go into any local community where they've been living in brick shacks because that's the only thing that they can afford or that they think is modern, and use natural resources that they find in their backyards, and at a very, very low cost, work with them to produce fascinating structures. So that's where I think there's a great opportunity to expand. And that's why we're now looking into moving into different parts. And I'm keen to maybe work with some of you guys in the future. The challenges are the skin. That's always difficult, because typically in bamboo structures, you'd use like grass or grass-like materials, but there you need to have a certain angle for the water to flow down. And when you're at the horizontal parts of it, there you'll get material rot very quickly. So within a shorter time, but like typically they would renew these roofs every 5 or 10 years anyway. But that's something that may come into play. The fabric itself, although in principle it's recyclable, the glass fiber reinforced polymer, but typically there's no infrastructure to recycle it. So it's quite wasteful potentially. But you can also clad it with metal sheets or with metal shingles. It all depends on how you want to do the waterproofing. But again, there's a lot of opportunities to tap into locally available resources and see where you go with things.
I have one more question.
Yeah.
You showed the diagram of how the radius were calculated and where the bending was becoming too significant near the singularity. And is there a way to negotiate and get the form so that you eliminate those radius and have a form without those compromised singularities? Compromise in terms of the radius being. So is there a workflow in which the Kangaroo is iteratively working to try and ease out those bends?
Let me share a screen here again. So, so in this diagram, it's still fully equidistant. And right now the weak spot is over here. That's kind of what yes, there are. We have drafted tools. I don't have them ready for today. What I was saying is if in the singularity here, you isolate the part here and you remove the requirement for your length constrictions to be fixed. And you allow your material, you allow the material to slide. Oh, hold on. I'm still in a different sharing mode. Hold on 1 second. Let me share like this. Yeah, now I can still see you guys. If you allow your edges here to become not fixed, let's say that our unit is 1. Let's say that all our edges, I need to look at these. Let's say that all of our edges are 1 unit fixed. But in this zone, we allow our edges to become different from it. Then what would happen is the bamboo would start to change. Like this red line here would probably want to find its balance somewhere closer over here. Oh, bad drawing. Let's probably do something like that.
Exactly, yeah.
And for that, what that would mean is that my length of 1 here would maybe become 0.9 over here. And that's possible. Like you can set that up in Kangaroo easily. Like currently, all our edges have the same stiffness in terms of the length compression. So we can remove all of these from that length compression and allow it to become totally free. The tricky thing is then that means that this part cannot be produced from a flat grid. It means that you need to make that 1 stick at a time. And that's possible again. Like you can cut out the singularity from your design ahead of time and make that one first. And produce all the rest as a flat grid, just like this. And produce your singularity ahead of time, and then you paste it in there. And that's how we had made our physical models that I've shown you earlier. And that would then again be with the layup method. So this center part would then be done 1 stick at a time, where you mark up the intersections, you connect it, and for the other parts you use the flatbed grid method. But the reality, so what that would mean is for this setup, it means that the oculus will become bigger.
Yes.
And for the triangulated part, if you'd have a triangulated singularity, it means that the triangle becomes much smaller. So there's still some constraints, but at least you can relax it a little bit. So one strategy is that. Another strategy is to split your bamboo ahead of time. You just cut your bamboo in half, and then you allow the parts to slide over each other. Or you make these parts out of bundles of splits, which is also possible, where you do it with bundles of splits, or you do it with bundles of smaller tubes, smaller combs only for those areas. All these things are ways to reduce the shear force. All of these reduce the shear force that you have inside your material. So it's either relaxing of the knots, or it's to do to change the shear force. Then that becomes possible again.
Understood.
Yeah.
Yeah.
So I have a question.
Yeah, go ahead.
We've been talking like all of these methods working on like a square grid. I'm wondering if we just like tried different kind of grids. Does it work, or it should be like only square grid?
This is a concept. Here in this studio, all the students were working with square grids, but this one here is actually using 3 directions. It's using a hexagonal grid. But then again, 2 of the directions operate as a flat bed, and the 3rd direction goes over to lock the squares into shape. Because what you need to have for your flatbed system to work, you need to have something that can hinge. And the minute you create a triangulated setup or a hexagonal setup, like a hexagonal setup would be something like this, or even an octagonal setup, you're bringing in triangles, and triangles basically lock in your hinges. So the hinging system doesn't work anymore. So in this model here, what they did is they started off with 2 directions, U and V, and then afterwards, they added the 3rd direction on it as a diagonal over the grid. So for the grids to pop up, you have to make sure that you continue your hingeability, and that can only be done if you don't have any diagonals in it. The diagonals lock in the system.
Yeah. Okay. Sounds good. Thank you.
Yeah.
Now, honestly, like many projects comes to my mind that makes more sense. I think Shigeru Ban also works with this method, maybe. Yeah.
So he did it. Well, the paper tube one that they did for the Hanover Expo was with Fraiotto, and that's exactly the same system. That one is actually a cheat. They actually ended up adding wooden arches in it because the paper wasn't strong enough. So they're actually cheating a little bit there.
Fake it till you make it.
Well,
Yeah.
Shigeru, did he? Fryoto got a Pritzker Prize. Did Shigeru Ban also get a Pritzker Prize? I think so, right? So if 2 Pritzker Prize winners are still faking it, they're
I
not
think,
going to get much further
yeah.
than that.
Fryoto got it like before he died with like 2 days. He was in his deathbed.
He knew he was getting it, but he never got the actual medal. He knew he was going to get it. He died between him being informed and then the people actually giving it to him.
That's sad, yeah.
Okay, so in terms of what's next, what I was thinking, what would be nice to do is because Digital Futures kind of wants to have a poster or maybe even a video at the very end. What I was thinking we could do is on Friday, I'm just going to introduce you to the Karamba setup. I still have to kind of prepare the file a little. I have to prepare the files a bit for that, so I'm not there yet. I'll see how far I can get because I'm kind of running out of time, but I can show you the files for sure. But in principle, that part is more informative as a design tool right now. Actually, at this point in time, we're pretty much there with the design tools and how to work around everything. So what I would maybe suggest is that everybody by Friday plays around with these tools and maybe designs a shell for themselves or a few shells for themselves. The actions that would require is working with the red, green, and blue surfaces that I showed and kind of make your own composition. You can work with columns. In order to create the offsets that you need to then, and eventually we, hold on, my brain is all over the place for a second, hold on. If in the end we want to make these types of drawings for everybody, which would be really nice, it does require the layers to be offset kind of in a certain way. I mentioned that the hack that I did to automate the offset here is kind of only working for this type of structure. If that means that you need to do things manually, if that means that you need to manually group your lines and then just bring it separately into Grasshopper to produce the offset, then that's fine. Like I would say for the final stage in terms of a design exercise, you don't have to have the full script working fully automatically, but it would be really nice if we can arrive at a setup where everybody has a 3D model that allows us to produce these types of drawings very quickly, very easily. The overlaps, don't worry about that. Like we have a script for that as well. I don't have it prepared to the point that it's ready here. We can just do it with continuous members. But it would be nice to kind of have these drawings and maybe have from everybody a 3D model that we could do a make 2D of. If we could get there by Friday end of day, then me on my end with my team here, we can maybe produce some videos of it. Like we can quickly just have a camera flying through it if they really want to, or we just at least produce a poster of it with some of these designs on it. I think that would be really nice. So yeah, if everybody who's here has time to do that, I think that would be a really fun thing to do. And then we just combine them all into one poster at the end. It'll be a good exercise for you to see where things work and where things stop working. My guess where things will stop working, I'm hoping that the Anemone curve joiner should work very well. For that to work well, all your input squares need to have the exact same orientation. Be careful there. And they need to touch very precisely so that the curves are actually going through the same points. The offsetting, there you might need to go manual, which is totally fine. You just do it manually, you bake it, you group them, you bring it back into Grasshopper and use offset with the surface normal. And then you just put the bamboo geometry on it that I mentioned. You can play around with that. And then we would have a geometry and we can do a make 2D. And then on Friday, I'll talk you through the principles of the Karamba script. And then I can give you some individual help with individual files if need be to make sure that everybody has a successful end product. And then that's it basically.
Sounds good. Can you just go back to the make 2D drawing, please?
Yeah.
Can you just
yeah, go ahead.
Can you just explain the logic of where to split it that you for the overlaps? What's the logic that you used?
Yes, I can. Hold on, I'm seeing if we have a quasi-clean script for that. I have a quasi-clean script for that, but it's not very clean. Let me just sketch here on the side. So if I have a curve, this is the normal vector of my surface that I've used to offset, right? I know my tangent vector here, so then I can do a cross product of these, and I can basically define my base plane that kind of runs over here, right? So I can do that for different parts. Oh, sorry. I can do that for different parts of my curve to kind of define my plane. So what I did is, once I have these planes, I can offset my curve left a little bit inside that plane and right, just by basically taking my control points here, moving that a little bit, and then redrawing my curve through it, right? So then what I have is bad drawing. Then what I have is two parallel lines. And then I just wrote a script that basically would draw this, and this, and this, and then this, by working with overlaps. So if I would split my original curve into the length that a normal pole would have, say 7 meters.
Okay,
7 meters. And then I would extend it 60 centimeters in that direction, extend it 60 centimeters in that direction. And then basically just then cull my lists, take one, the other, one, the other, one, the other, and that's it. So it's pretty straightforward. I don't think I have a clean version here.
Yeah, I think that's good enough. I just wanted to know where all are you breaking the line? Or so 7 meter point is good enough. 7 meter as the division factor is good enough for me.
Yeah, it's basically 20% overlap that we're typically working with, something like that.
Okay.
But again, at this point, it's more graphic, right? On site, you would test that yourself, but it helps in the graphic representation of your structures quite well. But the nice thing about it is by your original setup that you have your 2 poles or your 3 poles on different, bad drawing, that you have your 3 poles on different planes with the offset that you've done, is that you're basically creating your overlaps by redrawing your lines here and here and here and here. So your geometries are still not yet intersecting. So the knots still kind of work in terms of graphic representation.
So a single curve, when it's split into 3 segments because of the length, it's not really offsetting in the normal direction, but it's offsetting in the sideways.
Yes.
That's what you're saying. Okay.
Yes.
Got
So
it. The overlaps are sideways.
My original curve lies here in the middle. My original curve is, say, this one. And then, so that's U, that's V, that's W. 3 layers are offset normal to my mesh. So that's the normal vector to my mesh. And then in the plane that's perpendicular to the normal, but tangential to my curve, then I offset sideways left and right with the point, and I redraw the curve straight.
Got it.
Yeah?
Yeah.
Cool. Any other questions?
At least for me, I'll have to try to have more questions, but this is good so far.
Okay, well then I'll set up a folder where I'll try to put the recordings in, try to get that to you by the end of today. And then I'll see if I can prepare the files as much as possible for Friday. And then Friday will become a little bit more of a working session where the first half, I'll show you the Karamba stuff. And the second half, we'll deal more with the designs. I may not be able to give you all the tools to put your final designs into Karamba, because there's a few steps like creating the connectors in between it that I don't know if we have that cleaned up, but the concepts and the principles should be there for sure.
Also, Karamba is not a free software, so it's...
But you can have a free trial for 30 days, but I think
it has limited functionality. it has limited functionality. You can't
Yes.
use shells more than 64 lines. So
Yes.
we're anyways going to exceed that.
And the 64 lines is really small. 64 units anymore. Yes,
It's a joke.
yes, it's just to get you excited. Yeah, but then again, maybe you don't need it, right? This is kind of the advanced stuff when you start to talk to the engineers. Theoretically, your structural engineers would be doing that part for you. But it's interesting to start to see it coming together there as well.
I wonder if you recommend any resources to learn more about Karamba.
Say that again. What
If you recommend any resources for Karamba, I don't know. Do you have any recommendations for any like a resource online? Like websites or something?
Actually, the Karamba software comes with a very good set of example exercises that are quite self-explanatory, and the PDF that comes with it is really good as well. A lot of people have taught workshops on it, and I think you might find some tutorials here and there, but I don't know about a concentrated location. But the example files that they have are really, really good. And we're also going to use only a very small part of it. I'm not a Karamba expert, but it's not a difficult tool. If you want to use it in a casual architectural way, if you want to use it as a structural engineering tool, then of course you need to have a higher level of knowledge. For us, it's still a little bit more illustrative or decorative, let's say.
Just to add to that, you may follow Karambas on their social media platform. They keep hosting workshops, and because they are the developers, they are the right people to learn it from.
Yeah.
So I would suggest that will be the right way to go. But like Christoph mentioned, their documentation, the base documentation of any plugin is the best resource to learn it. And after that, the makers, if they do any workshop.
Yeah, in most of the workshops that they've been teaching lately, they're typically hooking it up to Galapagos or some evolutionary solvers, which is when it becomes really powerful on that end. But in our case here for these structures, there's no point really in combining evolutionary solvers on some of the parameters that we have. So for us, it's more of a end of the line frozen geometry calculation and then evaluating it. So in a way, you can bring it into any type of structural analysis tool, like if you're working with Robot or any of these other CAD softwares that structural engineers use. Typically, all you need to have is your axis model and then a clear data structure and then a definition of all the hinges and the joints that you have. So our setup is actually not Karamba specific. It's just because that's one that works in the Grasshopper environment. I know at Arab they were using a different software for it, and they used the same axis model that we had. At Bureau-Happold, it's also a different internal house software that they're using for it. So yeah, it's more illustrative.
Thank you.
Okay, so then for Friday, yeah, play around, try to come up with a nice structure. Don't per se go for scale, like try to go for something that looks good, where on one A0 poster, we can easily put like 8 or 10 or 12, how many we have, drawings from everybody. That would be really nice. And then I'm hoping to collect the 3D files from you at the end of that, and then I'll see what we have, if it's possible for us to make a video for that the week later. Enrique did his thesis with Karamba and C#. So yes, Enrique, maybe on Friday you can help me then. We'll see how that
C#. I heard C#, I guess.
Okay, guys, I have to run. I'll see you all on Friday morning, 9:30. So tomorrow there's no class. Tomorrow is the founding day of the China Republic. So in Hong Kong, it's very tense right now. There's 10,000 police on the street to prevent people from protesting. So let's see what happens by the news on Friday morning, if everything is still calm and peaceful in this revolutionary city that has been muffled in the past year and a half since the pandemic. I'm not going to talk. I'm not going to say more about that on screen here. All right. See you guys. See you all on Friday.
Bye.
Thank you.
Bye.
Thank you very much.
Thank you.
Thank you, the chair.